Hello, this is going to be the review of our study guide, or at least a partial review of the study guide. I am going through all the stoichiometry problems from the packet, and I'm going to take at least one problem from each section. Sometimes I'm going to take more than one, and I'm going to solve them and explain my thinking on the way so that you can see all the steps to each type of problem, and from there you should be able to attack the rest of the problems, and we're going to review them the day after. So let's start right into it. This is starting with the practice questions, asking you to identify the type of reaction and then asking you to balance the chemical equation. So the one I chose from here is this this guy, combustion of what looks like benzene to me, although it could just be, no, that's pretty much a benzene molecule. Anyway, it's an equation laid out, and you have to choose what type it is. So I'm going to remind you of your types here. You have 5 types. You have a synthesis reaction, which follows this format. A plus B goes to AB. You have a decomposition reaction, which is AB goes to A plus B. You have single replacement, which is A plus BC goes to AC plus B. You have double replacement, where you have AB plus CD goes to AD plus CB. And then you have a combustion reaction where some hydrocarbon, in this case it's going to be carbons and hydrogens, and you don't know how many, so I'll put a little N and an M there, just some amount of each, is going to react with oxygen, forming CO2 and water. Okay, those are your 5 types of reactions. So when I look at the reaction up above, the original one, C6H6 plus O2 goes to CO2 plus H2O, I think it fits pretty strongly into this category here. And I'll point out there are carbons and hydrogens in the original molecule, and they are being added to oxygens, which looks exactly like the bottom formula. And the telltale final products are carbon dioxide and water. Combustion reactions of hydrocarbons almost always end up with carbon dioxide and water. Okay, so I'm going to take that. Let's get rid of some of this stuff here. That is my reaction. I'm going to write a little combustion here. This is a combustion reaction. I can put that out front. But I also have to balance it. And right now I can tell it's not balanced because I see things like there are 6 carbons on the reactant side, but there's only 1 on the product side. So I need to go ahead and fix that. Whoops, that's not an eraser. That's an eraser. Okay. Okay, we'll go on. So what I can do is out front of each molecule, I can put a coefficient. I'm not allowed to touch these subscripts down here. I cannot change those. Those are fixed in stone. All I can do is multiply the number out front by a constant. Now I'm also going to notice some other things here, like the oxygen. If you see, there's an oxygen here, but there's also an oxygen here, and both of them are to the right of the arrow. Okay? So when you see that, I did it again. When you see that, you're going to balance those oxygens last. We want to save those to the end. We're going to choose all the elements that are not repeated on the same side. So I'll start with carbon. Carbon's an easy one. I see 6 carbons on the left. I see only 1 carbon on the right. In order to balance that, I need to put a 6 out front. Right there. That'll give me 6 carbons on the right, and if I look on the left, also 6 carbons. So my carbons should be finished after that. Now I'm going to go to my hydrogens. I see 6 on the left, and I see 2 on the right. 6 on the left, 2 on the right. So if I multiply the right side by 3, 3 times 2 should be 6 hydrogens. And that should give me an even number of hydrogens on both sides. So at this point, I should have everything taken care of other than the oxygens. So let me look on the left. 2 oxygens. On the right, I see right there, that's 2, but there was a 6 in front. So 2 times 6, I see 12 in the carbon dioxide. 12 on the right, plus you also have that guy there, that oxygen who's being multiplied by a 3. So I have 3 there, plus the 12 from the carbon dioxide. On the right side, I see 15 oxygens. So back over here, if I want to make that into a 15, I have to multiply it by 7.5, or 7.5. Now, this is technically balanced. However, you should never, a true chemist doesn't put halves in, doesn't put decimals in when they're balancing these things. To clear a half, I can multiply by 2, but I need to multiply the whole thing by 2. So if you ever find yourself with a fraction, if the fraction is a half or a third or something like this, you multiply it out to clear the fraction. So if I'm going to multiply everything in this equation by 2. So here I go. Let me get rid of these numbers. That's 7.5, 6, and 3. If I double them all, will become 15, 12, and 6. But don't forget there was a 1 in front of this over here, so I'm going to put a 2 there. I have to double that as well. Now, if you count everything up, that should balance out. So let's make sure. That's 12 carbons, 12 carbons, 12 hydrogens, 12 hydrogens, 30 oxygens. This over here is 12 by 2, so that's 24, plus 6 more oxygens right there. So 6 and 24 is 30 oxygens. So that is a balanced chemical reaction. Now I know it's messy, so let me actually rewrite this so that you can see it. This balanced would look like 2C6H6 plus 15O2 turning into 12 CO2s and 6 H2Os. Very standard. Got to be able to do this. If we can't balance a chemical reaction like this, then our stoichiometry is going nowhere. And we're going to see that in the problems to come. Okay? So, stepwise, just to reiterate, we figured out what type of reaction it was based on our 5 types of reactions here. And then we put coefficients in front to balance. All right, next problem. So if you're following along in the guide, this next problem is number 6 under the stoichiometry section. Excuse me, number 6 under the mole review section. This is a standard conversion problem. We've done a ton of these. It says how many grams in 7.8 times 10 to the 25th atoms of argon. So I'm going to point out 2 things that are really important in this question. First off, they give us a number, 7.8 times 10 to the 25th atoms of argon. I always take that number, put it right out in front to start with. 7.8 times 10 to the 25th atoms. Done. Okay? Then the other thing important in there is what they're asking for, and they're asking for how many grams. Sometimes they write it as calculate the grams in 7.8 times 10 to the 25th, so it doesn't always say how many. But for, you're always looking for a unit they give you. In this case, they give you atoms of argon and the unit they ask for, and they're asking for grams. All right, so we're going to do that. So when I do this, okay, when I do this, all of my conversions go the same way. I have this number out front, this 7.8 times 10 to the 25th atoms, and then I multiply that number by a fraction. I take the unit that I start with, the atoms, and I place that unit on the bottom of the fraction, And I do this without putting numbers in. I just put that straight up. And then I take the unit that I'm looking for. And in this case, they said how many grams. And I put that on top. And I like to include the chemical. In this case, I'm talking about the chemical argon. Okay. I have to turn, if there's grams involved, and in this case there are grams involved, if there's grams involved or molecules involved, I have to look my numbers up on the periodic table. Okay? The periodic table can tell you the following things. It tells you 1 mole on the periodic table, with a little PT there. It tells you 6.022 times 10 to the 23rd of atoms or molecules. Very good penmanship there. And it also tells us a molar mass. Call it a molar mass in grams. And the molar mass, of course, is the one written on the element box. It's the largest of the two numbers. Okay? So here I see I have to look up atoms and I have to look up grams. Well, atoms, I wrote that right here. 6.02 times 10 to the 23rd. So I'm going to take that number and put it right there in front of atoms. 6.022 times 10 to the 23rd. Right there in my fraction. The other unit was grams. And the molar mass I'm going to have to look up here is grams of argon. So I go to my periodic table, I look up argon, and I see that argon has a molar mass of 40. And I'm rounding this. 40 grams. Okay? So, once you've gotten this far, the rest is math. This is the chemistry. Now you just have to be able to multiply a fraction. So this is essentially what you're going to put into your calculator, and I'm going to make a further statement here. This is exactly like multiplying 7.8 times 10 to the 25th over 1 times 40 over 6.02 times 10 to the 23rd. So the two numbers on top get multiplied, the two numbers on bottom get multiplied, and then you divide top by bottom. Now you'll notice that I have 25 tens on top and 23 on bottom. I will recommend to you right now, your calculator is bad with tens. It just is. Most calculators, you have to be very careful about how you type your syntax in order to get them to even read tens properly, but you can do them in your head super fast. I have 25 up here, 23 down here, 25 on top, minus 23 on bottom. You're going to be left with, I'm going to cancel those out, I should be left with I should be left with 2 tens on top. That's it. So I'm going to pull those out. I'm going to leave those on the edge here. And now I'm just going to take the 7.8, multiply by the 40, and divide by the 6.022. And that will be a lot easier. And whatever comes out of that, I can multiply by my 10 squared. So let's do that in our calculator. So put that in my calculator, and I get 51.8. 51.81 if I'm being honest. Now, I could record that. If I look, 51.81 times 10 squared is a number. I can definitely put that in. This is technically correct. However, in scientific notation, that decimal place would be in the wrong spot. I want that decimal place to be one spot over here. I want it to be next to the 5. So if the 5 is the first number, the decimal place comes right after that first number. So I can write this in one of two ways if I want to be technically correct. Let me give myself some room to write this here. If I move that decimal place over, I would get something like this, 5.181. But that would give me another 10. I already had the 2 tens, so this would bump that up to a total of 3. Okay? And I would say that's grams of argon. But 3 tens is not that hard to multiply out. This is the same as if I did 5.181 times 10 to the third or times 1,000. I would just have 5,000 181 grams, or a little over 5 kilograms of argon. That's not that hard to write. The whole point of writing in scientific notation, make sure that looks like a comma. The whole point of writing in scientific notation is to take big numbers that are hard to read and make them easier to read. Well, this 5,000 is not that hard to read for most of us at this point. So I would actually accept either of these answers on a test. Okay? So our steps here. We found out what they gave us and what they wanted. What we gave went out front. That number went out front. We took that starting unit, put it on bottom. We took the unit they wanted, put it on top of the fraction. And our numbers came from the periodic table for this one. 1 mole, or 6 times 10 to the 23rd atoms, or the molar mass. In this case, it was molar mass in atoms. Now, just to make sure you're okay with these, I'm going to do another one. Oh, we have one more thing on the periodic table. That's actually going to show up in this next one. The periodic table also tells us that you have 22.4 liters of a gas at STP. STP is similar to saying room temperature. It's not actually room temperature, it's a little lower than that. It's 0 Celsius and atmospheric pressure, which is about 760 millimeters of mercury. We'll get to that in the gas chapter. But this was Avogadro's famous thing. You could figure out how big the balloon would be if you had a mole of gas in it. And that was his number, 22.4 liters. His number is actually the 6.022. All right, how many liters? And 84.3 moles of nitrogen gas at STP. Okay, let's do this one. So again, I'm going to look through and I'm going to find two things. I'm going to find the number they give me, in this case 84.3 moles of nitrogen, and then the unit they want, and they want liters. So here I go. That number they gave me goes out front, 84.3 moles of nitrogen times, and I give myself a fraction line. The unit they started me with, I'm going to put that to the bottom of the fraction. So in this case, moles of nitrogen go on bottom. The unit they want is going to go on top, in this case, liters of nitrogen. And then I check my periodic table for the numbers. And up here I can see I've got moles, which is 1, and I've got liters, which is 22.4. So we said that moles, it was 1 mole, and liters was 22.4. This is a little easier to put into a calculator because we don't have all those powers of 10. So I can just go ahead and do 84.3 times 22.4 and divide by 1. Let's do that in our calculators. And when I do that in my calculator, I get 1,888 liters. Big number. But not so big that we have to put it in scientific notation. I'm usually okay up to about, when you start to get into the 100,000s or the millions, then scientific notation makes more sense. Some people will do it for thousands. Just make sure you can read it. Okay, so again, process was still the same. Number they gave me up front. Fraction, where the unit I started with went away and the unit I wanted went on top. And I get a final answer. Keep in mind your final answer has a number, but it should also have a unit. In this case, my moles of nitrogen should go away and my unit should be liters of nitrogen. I can even put that in there, liters of nitrogen. Okay, that's a standard conversion. No, that's not what I want. I want this. Okay, we're going this way. All right. Move these over here so I have some space. Now we're on to the stoichiometry section. And I'm going to take one of the harder ones from the end. This is number 11 in the stoichiometry section. And I'm going to solve this one up. This one is a little bit more challenging than the others. One, because it starts with grams and ends with grams, so it's a longer stoichiometry problem. And two, they do not give you, not only do they not give you the formula, they don't even give you the complete list of reactants and products. So you're going to have to do a lot here. So let's go through it. I'm going to underline some things that I think are important. So I'll read it out. When half a gram of magnesium reacts with silver nitrate, how many grams of silver are prepared? Lots of stuff there. First thing I notice I don't have a chemical equation. I need to do that first. So I'm going to underline things that help me with the chemical equation. I see magnesium as part of the reaction. Silver nitrate is part of the reaction. Silver is part of the reaction. Okay? And then I have some other keywords. The word reacts is important. And then prepared is also important. So the word reacts is letting me know who my left side of the equation is. Who reacts with who combines with who. Sometimes they'll say combines or instead of reacts. But that's the left side of the arrow. So if the arrow's in the middle here, the left side should have magnesium and it should have silver nitrate. Now magnesium's easy because he's a pure element. You can just write magnesium. Silver nitrate, you have to make sure you know your charges. Silver here, and nitrate is NO3. Now, if you look silver up, or if you've done enough of these, silver is a +1 ion, nitrate is a -1 ion, so those are already balanced. You do not have to balance those. Okay? Every time. All right. So I'm going to then have to do the other side of the reaction. Well, when it says prepared is a key word saying that those are things that we made in the reaction, or those are products of the reaction. Those are the right side. So it says silver is prepared. So I know I'm going to be making silver on the right. Plus, there's got to be something else. If I start with magnesium and silver and nitrate, and I just make silver, something's up here. So I need another thing in there. Well, the leftover pieces look like a magnesium and a nitrate. Also, you can apply this. If we go back, we had 4 types. This looks like a single replacement reaction. The magnesium was by himself at the beginning, and he came up with a pair. Well, at the end, I should have another pair and a single. Okay, so as a single replacement reaction, here it is. If I end up with silver as my single dude, which the problem told me I did, I should also have magnesium. Whoops, change colors there. I should also have magnesium nitrate. But you got to be careful. The silver was a +1 ion, but a magnesium is a +2 ion. We can see this because he's in the second column on the periodic table. So if I only put one magnesium with one nitrate, that does not make magnesium nitrate. In other words, a +1 and a +2 and a -1 do not cancel out. I actually need 2 magnesiums. So I'm going to put a little parentheses around the magnesium and say I want 2 of him. That's better. Okay? So, this is my reaction, right there, and it's not balanced. If you look at the left side, I only have 1 nitrate, but on the right side I have 2. So to balance this, let me do this in a different color, I need 2 nitrates. But if I put a 2 there, that messes up my silvers, so I also need a 2 in front of the silver. There's a balanced reaction. All right? Always start with a balanced reaction and then go back and do the rest. Okay, here we are. Now I can start the actual stoichiometry problem. I see, now let's look for numbers. When half a gram of magnesium reacts, how many grams? So they're asking me to go from grams of magnesium to grams of silver. Okay, I can do this. Out front, my first number is the half, so 0.50 grams of magnesium. And I'm going to convert him, just like I did before, with a fraction. The unit I start with is grams, so grams are going on bottom. Now here, I can't go straight to grams of silver. I have to, if we were going to convert one guy to one other guy, when I'm changing elements, I have to use moles, and I'm not in moles yet. So before I can go anywhere, I have to change these into moles of magnesium. That has to be the first step, getting into moles. If you're already in moles, fine. But before you can change magnesium into silver, they both have to be in moles. So, grams into moles, grams of magnesium to moles of magnesium. I'm going to look that up on my periodic table. Well, the periodic table tells me 1 mole, and it tells me 24 grams of magnesium. Sweet. If you multiply that out, let's do that in our calculator. When I put that into my calculator, I get 0.0208 moles of magnesium. Okay. Now that's moles of magnesium. And now that I have moles of magnesium, I can change them into moles of silver. Goes like this. Let me give myself some room again. So this is now the number I know. I know that one here. I'm going to put that guy out front. 0.0208 moles of magnesium times my next conversion. Well, if I start with moles of magnesium, then I'm going to put them on the bottom of the fraction. And I'm trying to get to silver, so I have to get over here to moles of silver. Now, here's the step that does not come off the periodic table. Because moles are on top and bottom of the fraction, I have to look up here. I have to look at my balanced chemical equation for the coefficients. And my coefficients for the balanced chemical equation, magnesium had nothing in front of it, which is the same as a 1. Silver had a 2 in front of it. That's it. 2 moles of silver were equal to 1 mole of magnesium. And I can multiply that out. If I multiply that out in my calculator, I should get 0.0416 moles of silver, because the moles of magnesium will cancel. Okay, that got me to moles of silver. I'm almost done. They did want silver, but if you stop there, you're not answering the question. Remember, the question was how many grams of silver, not moles. So my last step is going to have to be changing that number of moles of silver into grams of silver. Once again, I know it now, so I'm going to put it out front. 0.0416. Is that a 6? Perfect penmanship. 0.0416 moles silver times, last thing I do is get it into grams. Well, moles is what I started with, so I put them on the bottom of the fraction. Grams is where I'm going, so they go on top. And because it's grams, I can look it up on the periodic table. Periodic table will tell me for silver that 1 mole, I believe, is 107. Look at my periodic table here. Yep, 107.8. I'll actually round that to 108. 108. And if we put that into our calculator, I get 4.49 grams of silver. Okay, that's a standard stoichiometry problem. We started up here with the unit they gave us, 0.5 gram of magnesium. We had to change that into moles first so that we could use the moles of magnesium to convert to moles of silver. Okay, because this chemical equation, magnesium plus 2 silver nitrate goes to silver plus magnesium nitrate, that equation is only good in moles. It only tells us moles or molecules. It cannot tell us grams. Okay, so once we were there, we were able to get moles of silver, and then we took those moles of silver and we can use the periodic table to change that back into grams of silver. Very useful. All right, almost done. Sorry, just a little crowded here, I can tell. Okay. Second to last problem that I'm going to show you. we have 3.45 moles of nitrogen reacting with 4.85 moles of hydrogen to form ammonia. This is out of the limiting reactant section, number 2. And they want to know how many moles will form and what is the limiting reactant. Well, this is another equation that did not give us the chemical reaction. Another problem that didn't give us the chemical reaction. Fortunately, though, it tells us all the pieces. It doesn't always tell us the pieces. It says nitrogen reacts with hydrogen, don't forget the reacts part, and it forms ammonia. So when I do my arrow, here's my arrow, the reactants on the left should be everything that said reacts. So nitrogen, which we know is N2, make sure you know nitrogen is always diatomic, reacts with hydrogen, which is also diatomic, and forms ammonia, which if you don't know by now is NH3. Balance this puppy up. I have 2 nitrogens on the left and 1 on the right, so I need a 2 here to balance the nitrogens. That 2 gives me 6 hydrogens on the right, 2 on the left. I need a 3 to balance my hydrogens, which must mean that there's a 1 in front of the nitrogen. Check with yourself to make sure that's true. And there are actually, so a limiting reactant problem is always going to give you 2 numbers, at least. So they give us almost 3.5 moles of nitrogen, and they give us almost 5 moles of hydrogen. Your job is to figure out which one produces less ammonia. The one who produces less ammonia will be limiting and will determine how much you form. You can only form as much ammonia as your limiting reactant provides. So we're going to do 2 conversions to try and figure out our ammonia. Our first conversion is the 3.5 moles of nitrogen. So I'm going to write that right here. 3.45 moles N2 times. Well, if I start with moles N2, they have to go bottom. And then they're asking for moles of ammonia. How many will I make? How many moles of ammonia will form? So I'm going to put those up top. Moles NH3. Now the numbers, again, for moles, if I have moles on bottom, moles on top, those numbers come from my balanced chemical equation. N2 had a 1 in front of it. NH3 had a 2 in front of it. Okay. 3.45 times 2 divided by 1 should give you 6.9 moles NH3. Now, we're not done, though. That's one of the 2 things I had to make, but the other one was 4.85 moles of hydrogen. So let's go down here and do that. 4.85 moles of hydrogen. Convert that times fraction. If I start with moles hydrogen, then moles hydrogen have to go on bottom. I'm trying to get ammonia, so I'm going to put moles, let me see if I can write this, NH3 on top. And then, because it's moles over moles, I get my numbers for my balanced equation. Well, hydrogen had a 3 in front of it. NH3 had a 2 in front of it. Okay, so this becomes 4.85 times 2 divided by 3. So let's put that in our calculators. And we come up with 3.23 moles of ammonia. 2 perfectly good conversions, but we haven't answered our question yet, so let's go back up and remind ourselves how many moles of ammonia will form and what is the limiting reactant. Okay, in both cases, it's the lower of the 2 numbers. So if I have this much nitrogen, I should be able to make 6.9 moles of ammonia. If I have this much hydrogen, I should be able to make 3.23 moles of ammonia. Well, if I can only make this much ammonia, I can't make 6 or 6.9. So 3.23 is how much I make, and the limiting reactant is the one that I made it from, so the hydrogen. I ran out of hydrogen before I ran out of nitrogen. Notice that it was not the reactant with the smaller number of moles to start with. I actually had more hydrogen than, in terms of molecules and moles, than I had nitrogen, but I still ran out of it first because it took 3 times as much hydrogen to make the ammonia as it took the nitrogen. Okay. Last one. Oops, I've got to do this. So this is number 1 off of the percent yield section. This one they give us an equation for, and it's balanced. We can be thankful for that. It's less work to do. If we start with 389.4 grams of aluminum sulfate and you isolate 212.4 grams of sodium sulfate, what's your percent yield? Anytime you see that, percent yield, you got to think, I need 2 numbers. I need an actual and I need a theoretical. There it is. And you're going to be multiplying that times 100. Okay, so looking through this equation, start with, okay, this is not one of the 2 numbers, the actual or the theoretical. This is a starting point that we have to convert. All right, the other number they gave us, you isolate this. If you isolated that, if you produced that, if you created that, that's actually something that happened. You actually made that. It's almost always a product, okay, that they're going to say this for. And sure enough, sodium sulfate is a product, but it says you did make this, so that is an actual. So they give us this number. You will never have to calculate an actual, usually. I mean, they might tell you that you have a weighing boat that weighs 5 grams, and then you put your product in it and it weighs 12 grams. Then your actual is, how much was there, it was 7 grams. But other than that, you're not going to do much calculation. So I can already take my equation, let's do this, and say 212.4. So on top of my equation, it's going to be 212.4 grams on top, multiplied by 100. So all I have to do now is solve for my theoretical yield. If I can solve for that, I can put it on bottom and I can do my calculation. Let's look. The only other number in there, besides the 212.4, is the 384.4 grams of aluminum sulfate. All I have to do is convert that aluminum sulfate into how much sodium sulfate I should have made. That's a math calculation. And because it's math, it should give me the theoretical yield. So let's take that 389.4, and put it out front. Okay? Let's change color there. 389.4 grams of aluminum sulfate. Times. I'm going to get rid of grams, and I have to get moles. Remember, in order to use our balanced equation to convert something, we have to be in moles. So let's look up grams of aluminum sulfate on the periodic table. I know it's going to be 1 mole of aluminum sulfate. And I get 342 grams for aluminum sulfate. So when I do this conversion, I get 1.14 moles of aluminum sulfate. That's going to be my new front number. So let's put it up front. 1.14 moles of aluminum sulfate. Okay, next part of the conversion. Just like all stoichiometry, if I start with moles, I have to get rid of them. Moles aluminum sulfate. And on top, I'm trying to get moles of sodium sulfate. Actually, I'm trying to get grams of sodium sulfate, but I have to go through moles first. So moles of sodium sulfate. And I looked that up in my balanced chemical reaction. Well, aluminum sulfate is here, sodium sulfate is here. The sodium sulfate has a 3 in front of it, the aluminum sulfate has nothing in front of it, so that's a 1. So it's a 3-to-1 ratio. 3 sodium sulfates to 1 aluminum sulfate. Multiply that out, and I should get 3.42 moles of sodium sulfate. Okay. Almost done. Last bit. I'm going to take that number, and he's going to be up front now, and 3.42 moles of sodium sulfate times. Okay, last bit. Just got to change it back into grams. So put moles on bottom. Sodium sulfate. Grams on top. Sodium sulfate. Let's see if I can write my 2 there. All right. Periodic table tells me it's 1 mole. And for grams, I got to look that up. And for sodium sulfate, it's 142. And now you just have to take your calculator and do 3.42 multiplied by 142 and divide that by 1. And you should get something like 486, if I round it, 486 grams of sodium sulfate. Now that was all math. So because it was a math calculation that gave me that number, that is a theoretical yield, 486. So I'm going to go back up here. Theoretical went on bottom, remember? So that was me calculating my bottom number, 486. 486. Okay. So now I can take top number, this is a grams, top number divided by bottom number times 100. We'll do that in our calculators. So 212.4 divided by 486, and I get, and multiply by 100, I get about 43.7%, or about 44%. Not a great yield. That's okay. So, steps. We did, the actual was given to us. That was up here on the problem, the 212.4 grams of sodium sulfate. The theoretical had to be calculated. In other words, it was a stoichiometric conversion, starting with the number they gave us and converting it to the unit that we had, that the actual was in. So the actual is going to be given. We just need to convert the other number into that unit. And the actual was on top, theoretical on bottom, times 100. Okay. You should be able to use this technique, those techniques I've outlined in this review, to get through the whole packet. And good luck.